the energy and hydraulic grade lines. I know we went over this on Tuesday, but I wanted to go back over this to talk a little bit about some, in particular, with respect to the cases that we showed. I just wanted to articulate some of the important nuances of what we're seeing in how the energy line and hydraulic grade lines are drawn and what they're telling us. So we talked about this in terms of the Bernoulli equation. The terms of the Bernoulli equation can be interpreted graphically using the concepts of the hydraulic grade line and the energy line, where the hydraulic grade line is everything in Bernoulli equation except for the velocity head, right? And the energy line is all three forms of energy at all points along a flow path, along a pipe that wiggles, whatever. We'll talk about those here in a moment. It's weird, my arrow didn't work. Right? We'll do that. Okay, so the energy line is H, where capital H is the sum of all of our energies. We haven't really designated it that, but we'll start to do that now. So it's total big H here. And then the HGL, the hydraulic grade line, is some distance Z plus rho over G. So in other words, pressure over gamma. And so Z is, of course, our potential energy, and P over gamma is our pressure energy, right? So that's also what we call hydraulic head. That was something that we stated back when we were talking about hydrostatics. So that hydraulic head is now providing for us a hydraulic grade line. When we add the kinematic piece, the kinetic piece, that's when we add V squared over 2G, and that gets us another actual length above that to get to the energy line. Right. So our total head, as we've talked about many times now, P over gamma plus V squared over 2G plus Z is constant along a streamline in the context of the Bernoulli equation, and provides us with H everywhere. So the energy lines are a little bit boring at the moment. They're just horizontal because we're not losing energy anywhere. We haven't talked about energy losses, and we'll get to that in a little bit. But in fact, at the end of the slides today, I'll just provide you with one small example of what that'll look like. But so right now, we're not calling that an energy grade line. It's a hydraulic grade line, though, when we see the hydraulic head, these two pieces, the potential energy and the pressure energy, changing because of changes in, there's some changing because of the change in the velocity for some reason, which of course influences the velocity head. Okay, so so the difference, as we've talked about then, between these two is really V squared over 2G, or the velocity head. So let's put that into context a little bit. Again, as we had on the previous slide, I got to get into pen mode here. I'm going to go with blue. So H is equal to P over gamma plus V squared over 2G. I'm hoping that repetition will get this ingrained into all of our heads, plus Z, right? And so if H is the total energy, H1 is equal to some H2 is equal to some H3, et cetera, along the flow path or streamline of interest. So let's go back to these three examples I showed you sort of quickly at the end of class on Tuesday to just talk through them a little bit. So the first one looked like this, and there are a couple of things going on here, and I just wanted to more carefully write them out a little bit. So here's point number one, right? Somewhere back here is point one, and over here more or less is point number two. And what we know about this pipe, what we're being shown is that the diameter is decreasing. But regardless of that, we know from mass balance that Q1 has to equal Q2, right? So Q1 equals Q2. We know that both of these can be broken down to A1 V1 is equal to A2 V2. And because the diameter of the cross-section of this pipe is shown to be decreasing from 1 to 2, so in other words, D1 is greater than D2, we then would surmise that A1 is greater than A2, right? And if we go back to that continuity equation up at the top, it says A1 V1 equals A2 V2, then V2 will have to compensate here for this change in cross-sectional area. Oops, I didn't mean A, this should be a V1. So V2 has to be greater than V1 because A1 is bigger than A2, all right? So if that all makes sense, then we would expect, and as we see here depicted, the velocity head is fairly small at point number 1, and it gets bigger at point number 2, right? I guess that was the wrong place. V2 squared over 2g is actually indicated over there, not in the middle. But in any event, you can see that we go from a small v squared over 2g at 1 to a larger velocity head at point number 2. And because of that, then we also have to have some commensurate changes in either the pressure head or the potential head. Now, the potential head is usually fixed. This elevation head Z, or potential head, that is typically fixed, right? We're not, the pipe is not going to suddenly adjust its angle and how it's situated in space simply because velocity head has changed. So it's usually the pressure head that takes on that big change. So we are fixed with Z1 and Z2 being two different elevations here, right? Two different values. So there is some change in Z, but regardless of what's happening with V and P, those are fairly static, right? The changes in elevation are pretty fixed. So then the P over gamma has to respond. And so what we see is that for, our hydraulic head for starters is this dashed line. The hydraulic grade line is the dashed line dropping down, and it's responding to changes in the velocity head, right? And so just to summarize this, from 1 to 2, we are getting a fixed increase in Z, which is given. We surmise that V has to increase, the velocity has to increase because of the change in the diameter of the pipe, and therefore we expect that the pressure has to drop, right? The pressure head, or which is just P over gamma. Gamma is not changing. We're not changing the type of fluid we have. Therefore, the pressure has to drop as well. And so this is part of the beauty of the Bernoulli equation, is that just relating these three things at one point to another allows us to think through how these energy relationships and these quantities that are built into them are changing along a flow line. All right. The other thing I want to point out is note what's happening between the stagnation tubes right here and the static tubes here, okay? The static tubes are providing us with the elevation of the hydraulic grade line, and the stagnation tubes are providing us with the total energy, okay? The energy line. So across wherever we put a stagnation tube, we should have the rise of the water in that tube always come up to the energy line. All right, so that's an important aspect as well. If we want to measure the velocity head, then one easy way to do it is to insert both, or instrument our flow or our apparatus with a stagnation tube and a static tube to be able to measure that difference. And this difference here is that velocity head, right? And that exists all along the pipe. Okay, so that's where we're going with this concept, that we can apply Bernoulli's equation at all places to learn something about how all of these energies vary amongst each other. Okay, so
clarify something from that last slide.
Sure. Let's see if I can go back there. There we go.
I thought for stagnation tubes the velocity was 0 right at like the entrance, and now we're talking.
Yeah, good. So that's a good question. So what's actually happening here is you still get so if you were to look at, there is still a full pressure, a full energy that is represented there. It's when we apply the Bernoulli equation right out in front that we would say that V is equal to 0 right in front of it, but that head is still being provided up the tube. Let me think of a better way to say that. So the streamline that moves along the center, I guess I can actually draw that. So the streamline that comes along here has to end up splitting, right? Part of it either has to go above or below or around to the side of this stagnation tube. So when we use the stagnation tube approach, we can say that the point right in front is V equals 0, but we're still getting the full energy push reflected in the standpipe that is connected to it. That's connected to the middle. Does that help a little bit? So you're still getting the force of all the velocity moving in that direction. It's just that when we apply it to that micro spot, V squared, or velocity is 0 at that point.
Great, thank you.
You bet. You may not have been the only one with that question, so I'm glad you asked it. Okay. I want to make an important point with respect to this diagram. In the previous diagram, we didn't have a reservoir, right? We just water's coming from somewhere going up a pipe that is oriented, flowing upwards. In this case, in example 2, we have a slightly different situation where now we have this reservoir on the left-hand side, right? So at point number 1, indicated over here, you can see V1 and P1 are equal to 0. That's something that we've talked about before. And the energy line and hydraulic grade line are both meant to be coincident with this water surface. And the reason for that is that our total energy inside of the reservoir is basically represented by the elevation of the water surface. Okay, so dams let out water generally, at some depth, and the idea for that is that this is the energy, for example, I guess from P1 or from location number 1 to location number 3. That is the amount of energy that you can recover somehow from the dam. Okay, so in this case, a dam, of course, is going to have a lot of resistance in it. You're going to try to spin turbines and stuff that are going to take energy out of the flow. So that's something we'll talk about. Actually, in hydraulics, you'll talk about that a bit more. And in this case, we're just looking at here's the total energy going across. So it didn't change from where we started inside the reservoir, okay? And then we had, as we go into this pipe, we have a drop off because of this changing diameter, okay? So we have a drop off here until we get to sort of a more consistent diameter here. I'm just going to call it D2 because point number 2 is in there, but some diameter there. And then we're pretty consistent, right? So here's the hydraulic grade line going across. And then when we have the change in diameter again, V squared over 2G, in this case, V3 squared over 2G, that velocity head increases again because, again, Q2 is equal to Q3, right? Those flows have to be the same when we close down the diameter or we make the area smaller, velocity has to increase. And so that's what's represented here as the velocity head increases. Now, one thing you might be asking yourself is why does the hydraulic grade line go to basically 0, or rather, why does it go to the middle of the pipe in this case? So what's happening here is P3, you'll note, is equal to 0 because we have this jet here. Z3 still exists, right, to get us to the center of this pipe. And Z2 and Z3 are the same, but because P3 is equal to 0, essentially at this outlet, that means that, and we're not accounting for any losses here, so we're assuming we have no friction in our flow and all of that. That means that our hydraulic grade line is basically, after we get into this part of the pipe, it goes to the pressure part of this goes to 0 because we're connected to the outlet. When we start accounting for losses, we'll see that that's not really true. Like we would account for some friction along the length of this pipe. But for now, because we've simplified this this case a little bit, clearly we end up with only the potential energy and the contributing to the hydraulic grade line, and then the total energy is just our potential energy plus the kinetic energy. So EL, remember, is going to be equal to H at all places along here. And the hydraulic grade line changes because V changes along the flow, the streamline. And so B changes in response. Oops. Gosh, that was a G. Well, the other thing I miss about chalkboards or whiteboards is that I can write at a normal speed. So, all right.
Question about that real fast.
Sure.
You're saying that because the diameter of the pipe decreases, then obviously the velocity will increase. And then is that why even like inside that pipe, not necessarily on the outside, P3 would also be equal to 0?
At the end of this pipe, let's just call it section 3. Right. The reason that you go to P3 being equal to 0 is because we get the jet at the end.
Exactly. So on the inside of that, like third section of the pipe, then is the pressure not equal to 0?
So in this case, because of the assumptions we made for the flow being like non-viscous and all that, yes, it is 0 until you get back to here, where you just get out of the influence of that contraction.
Okay. All right. Yeah. That makes sense. Thank you.
Sure. All right. Any other questions on this one before we go to example 3? Okay. All right. Now with example 3, again, our energy line is constant, but we have this really like roller coaster ride of the pipe here, right? So again, we have a reservoir. So once again, we take the surface of this reservoir, and that is our starting energy line and our starting hydraulic grade line. And so what you see often with hydraulic grade lines is just as you come out of into the pipe, you see this transition that occurs. And that transition is occurring like kind of at a like entrance effects. So just, within a couple of, centimeters or inches, you would basically transition to the flow becoming more consistent and getting away from the edge effects of getting out of the reservoir and into this pipe. And so what you see then is, here is our, as is shown over on the right, this is our velocity head, right? V squared over 2G. And then you've also got this weird thing where our Z is constantly changing, right? Z is high here. It drops down to here. So there's Z, right, at this location. And the offset here to get us back to our hydraulic grade line is P over gamma, right? And so I guess that's shown over here too. I guess could have looked a little more closely at that. But in any event, these two are trading off as you go along this whole length of the pipe. Now, the diameter of the pipe does not change. Therefore, V squared over 2G, our velocity head, is constant because V is constant, and that happens because the diameter is constant. Right? Even though the pipe is, undulating sort of up and down, it doesn't have an influence on velocity at all, the way we are treating this flow. And therefore, we have this consistent sort of trade-off as you move down between the elevation head and the pressure head. So Z and P, basically pressure, are trading off. Really? It was a T. With their changes through the as you go down the pipe. Okay. Now, in a way, we could say that again, Z is fixed. Like the pattern of Z through space is this pipe is not necessarily, we expect it's not flexible, it's being held in place. And therefore it's the pressure that's really responding to this, the undulations in Z or the changes in Z. The velocity head is fixed throughout. So that is a fixed distance between the energy line and the hydraulic grade line. And the hydraulic grade line is dictating how Z changes are affecting P changes, pressure changes. Now, one thing to note, here's a point where Z is above the potential energy head is above the hydraulic grade line. Therefore, the pressure energy is negative, right? So you can have a negative pressure. Negative, now remember, this is going to be negative with respect to gauge pressure. So it just happens to be lower than the atmospheric pressure. It's not less than absolute zero pressure, but it is lower than the pressure outside, the atmospheric pressure. Okay, so really? D, that's supposed to be an F. D of pipe is constant. My goodness. I'm thinking that calling this a writing pad is a little bit of a misnomer. Okay, let's put our new knowledge to a test here and try to figure out what's going on in this particular problem. So let me move this guy out of the way. Okay, so a smooth plastic 10-meter long garden hose with an inside diameter of 20 millimeters is used to drain a wading pond as shown in the figure. So here's our little pond, here's the garden hose, and it's basically draped and sort of let to go downhill. And so we're given, this change in elevation of 0.23 meters. And the question then is, which one of these 1, 2, 3, 4, 5 lines represents the energy line and which one represents the hydraulic grade line? Okay, so tell me what your thoughts are if anybody wants to jump in. Let's start with the energy line. Which one of these do you think is the energy line?
Would the orange be the energy line since it's the height of the reservoir?
Yeah, so what number is that for anybody who might be colorblind?
Oh, that's 5, sorry.
Yeah, sorry, yeah, you do have to have good eyes, though, if you're whatever that is, that number, that's a 5. Okay, right. Yes, 5 would be the energy line because we're starting at the elevation of the water inside this little kiddie pool, or what was it called, the wading pool, and we stay consistent throughout. And the reason that we can, obviously, we need to be consistent throughout. So there's no surprises here that there's any removal of water or anything like that. So we're going to stay horizontal with our energy line. So this is our energy line right there, number 5. Great. Now, which one of these is a reasonable hydraulic grade line? 1, 2, 3, or 4. We're going to omit 5 because that's our energy line, and we assume they're not going to be exactly the same. We have to have moving water here, so there must be some difference between EL and HGL. What are your thoughts about a hydraulic grade line? Anyone?
1.
1. All right. Why do you like 1?
Just because on the other examples, it was kind of an instant change whenever the diameter changed of kind of where the water's going, or I guess the cross-sectional area. Mm-hmm. And then it stayed constant to where the end of the pipe was, as long as the diameter didn't change.
Yeah, exactly. Okay, so 1 is the right answer, and the reason is I maybe wouldn't have drawn it starting right back here. Like it probably needs to start coincident with the tubing or the garden hose, but that's a small edit here, small criticism. But yeah, one works out as our hydraulic grade line because we expect to have consistent velocity inside the garden hose as long as from the information we're given, right? There's no change in size. Therefore, we have to have a consistent offset in between the EL, the energy line, and the hydraulic grade line, which is represented by, again, V squared over 2G, right? Our velocity head. And when we do that, because the energy line is horizontal, it turns out our hydraulic grade line is also going to be horizontal. So 2, 3, and 4 have curvature to them. And there's no good way for us to explain the curvature or the change in the velocity head that is implied by those curvatures. So that's another way to think about it, perhaps to get to a, omitting the other possibilities to get to 1 as the possibility. So great. Okay, wonderful. All right, in this case, I'm going to draw these two in, the energy line and the hydraulic grade line. So let's read the problem statement. Water flows from a large tank as shown in the figure below. Atmospheric pressure is 14.5 psi atmospheric, or absolute rather. And the vapor pressure for water is 1.6 psi absolute. Viscous effects are neglected, and height h is one of cavitation begins. I guess it's a little choppy there on the English. Sorry about that. Which one represents the energy line? Oh, this was actually a multiple choice one, and instead I wanted to draw this one in together. So we're going to start with our energy line and hydraulic grade line right here, right? Because the reservoir on the left-hand side tells us that all the energy we have right now is equivalent to the top of the water surface. All right, so that's where we're going to go with our energy line. Now, let's start with the energy line, and I will switch colors for the hydraulic grade line. But as we've seen in all of the cases, I'm looking for a straight edge so I can make this as straight as possible. Well, let me see, I'll use this pencil. Interesting, I'm using 2 different writing tools here. All right, so I'm going to go straight across here. And essentially, this is our energy line, right? And I take it right. I mean, I guess I could take it a little bit further through that free jet to kind of get us a little further out there. But our energy line is going to be horizontal, and it will be the sum of our energy all the way across this system. Okay, so I'm letting the system be defined from the beginning of the pipe at the end of the reservoir to the end of the jet that's coming out of this pipe. Okay, what happens in this pipe? We've got some funkiness here, right? We have some changes in diameter, which will result in some changes in our velocities, right? So let me change color on my pen, and I want to ask you, where do you think I should go with our hydraulic grade line? We're going to go below the energy line, right? And if we think about the first part of this pipe, we're going to drop down, and then we're going to level out, right? We're going to come across, that's meant to be level. And now, what's going on here? Now we've got energy velocity increasing as we get into this contraction. Then we have a little neck that's a really small diameter. So we go from 4-inch diameter to 1-inch diameter. And then we go back to 4 inches, where D2 is noted as this 2-inch at the very end. So we'll deal with that in a second. But what this means then is when we get here, so V1 is greater than, let's do it this way. I don't like their numbering. Let's call this A, and this B, and then C. And for the sake of completeness, I'll call that D. So VA is going to be greater than or less than VB. What do you guys think?
Less than.
Less than, right? Because it has the larger diameter, larger area. So VA will be less than VB, which means that the velocity head in B will be greater than the velocity head in A. So what happens here is as we start to increase the velocity head and the velocity in the system, we're going to dip down and then we're going to come back up on the other side. So this is how the velocity head is changing. It's consistent back here, this, VA squared over 2G. The middle of this this constriction now is VB squared over 2G, right? And it is going to be a bigger value because VB is bigger than VA, right? Now, VC is going to basically, we expect to be the same as VA. And so it too will be less than VB, right? So I go back to having, roughly the same velocity head or difference between my energy line and my hydraulic grade line as I move across this part of the pipe. And then what happens here? Now I get to another place where I have another constriction and I get down to this sort of 2-inch diameter. What happens here is we just drop off and I'm just sort of estimating that to be less than this total change, right? The velocity VD is less than VB in this case, right? Just because it's going to be greater than VC, greater than VA, but less than VB because the diameter here is 2 inches, not 1 inch, right? That's where we have, so the highest velocity occurs in this little neck here at B. So B will be the highest velocity, VB. So this is now, this distance here is VD squared over 2G, which will kind of be where it ends. Now, I'm going to stop drawing it there. Ultimately, when we get into this this jet, we're probably going to end up with something consistent, but our pressure will go to zero and so forth. We don't usually draw our hydraulic grade lines and energy lines out into the jets like this, like the way I drew the energy line, in part because we're kind of in the uncontrolled part of the system. We've designed the system in a particular way for a particular distribution of energy within the pipes. And after it comes out, we may not care quite so much about exactly what goes on. So that's kind of beyond the system boundary in most cases. All right. Any questions on that before we move on? Why I drew it that way? Admittedly, it could have been drawn better, but regardless, I hope the main features are there, that they're easy to understand. Okay. One of the things that was in your book that I forgot to look really closely at the notes to see if I skipped this in sequence last week, but is this concept of vena contracta. So one of the things that's important about fluids is that they don't really like to make hard turns. They don't like to make sharp corners. And so what happens when you have a jet like this is, particularly when you have this sort of a shape on your at your exit, right? This really sharp shape. What you're forcing the molecules of water to do, or these streamlines to do, is make a really hard bend when you're, right in this area and right in this area, right? And so if the tank nozzle or an opening to the atmosphere is not smooth and well contoured, in other words, providing sort of a smoother transition between this flow regime here and this flow regime, whether it's in the jet or a pipe, then in this case, we'll work with the jet diameter. The jet diameter which we have noted here as D sub j, will be or is less than the hole diameter which is D sub h. So you can see D sub h listed over here. It's just removed a little bit to the left to make this a little easier to look at. So what that means is if you wanted a particular flow rate, and so you controlled the size of that hole, figuring that's your area, you're not getting that full area when you have a sharp opening like this, okay? So your actual cross-sectional area is dictated more by this vena contracta, and we'll talk about there are some standard ratios for this here in a moment. This phenomena is called vena contracta, and it results because, because fluids cannot turn sharp corners. Okay. So what do we do about this? Well, it turns out that there is a way of predicting, more or less, what this impact is going to be. And so here are 4 cases on the right-hand side. We looked at the top left one, this what we call a knife edge on the previous slide, and we calculate something called the contraction coefficient, C sub C. And that's equal to basically the jet, not diameter, but area, divided by the whole area. Okay? So what we're saying then with this knife edge is that a contraction coefficient is 0.61. You have 61% of your whole area is your jet. Okay, so you're missing on, if you try to control the size of this for a particular flow rate, knowing approximately what velocity you'd get out of it, you're missing 39%. That's a pretty big number, right? That's a big difference in what you might be expecting compared to what you're getting. On the right-hand side, at the top here, B, this is a well-rounded transition. These are, by the way, I want to say this is figure 3.12 in your textbook. So I just pulled it straight out of there. So this whole section exists in your book. This C sub C is 1, and that is because we have provided this. We've taken that corner and not made it real sharp, right? So we've tried to get into more of a smooth transition such that the streamlines can follow this change from the sort of reservoir flow condition on the left to the pipe condition on the right. This sharp edge transition here is the same as the knife edge, C sub C of 0.61. And if we end up with a reentrant setup, in this case now, we have a pretty sharp edge. It's sort of moved back, which means that you may be looking at flow lines or streamlines trying to do something like that, right? It's more than a 90-degree angle. Like this is a really sharp, hard turn, and therefore your C sub C, your contraction coefficient, goes down even more. So now you're at half of what you may have expected. So C sub C ultimately depends on what we might call the sharpness of turns or openings. Which I hope is the lesson you kind of learned from us going through these 4 examples on the right-hand side. So the well-rounded one, not a real sharp turn. We can maintain most, if not all, of the sort of energy, I guess, that we're transmitting there, and make sure that we're not trying to force fluids to do something they're not very good at. All right.
Are all sharp edges and knife edges, will they all have that same contraction coefficient, or does it depend on?
It probably, you could. So one thing we don't show, for example, is so up here on knife edge, if we cut this off, flat, that one would probably be a little bit intermediate for the sake of the questions or the problems that you'll be coming across. You can just use these for alt knife edge or sharp edge.
Okay, perfect. Thank you.
You bet. Okay. Let's go back to cavitation for a moment. And I just want to remind you of what it is, but I want to put it in the context of the Bernoulli equation, which is something you did for one of the problems in your homework. And we're going to work through a problem together, but it's going to come up in your next homework, and I just want to explain it and go through an example so that you can understand where this is coming from. So remember that, of course, we say, P over gamma plus V1 squared over, or let's get rid of the 1, V squared over 2G plus Z is equal to some constant along a streamline. Assuming that Z1 or Z is roughly constant, if V is also or tends to increase, then what happens to P? Of course, we expect P has to decrease. Now, in general, that's not a big deal. However, if you have such a big change in velocity that your pressure drops potentially to cavitation, then you've got a problem. Okay, when you get to when you get to its what is that pressure? To its vapor pressure, then you've got the potential for cavitation. Sorry, that's not, we don't really call that pressure cavitation, but it's vapor pressure that we have to worry about. Okay, so this could happen in a pipe. Including this, motor, underwater motor on these fins on the right hand side, to note that it can also happen in just an open water system. What you can see here actually these are all bubbles that are forming because of cavitation occurring, right? The blade is spinning so fast that the water right around it is basically being dropped to a pressure that exceeds or goes below the vapor pressure, and that's when we have these this cavitation occurring. All right, so what does it look like in a pipe? In general, the increases in V result in decreases in P, right? Increases in velocity result in increases or decreases, in pressure. And if the velocity increases are substantial, the pressure decreases can lead to cavitation. Gosh, I do know how to write. You wouldn't know it looking at this. Lead to cavitation. And the reason for that, again, is because our limit is ultimately in the pressure drop is our vapor pressure, right? So, and vapor pressures are going to differ for different types of fluids, different types of liquids. So in this case, here is the Vapor pressure noted, it's usually a very low pressure. It's a small pressure. And with a small flow rate and therefore not a huge velocity through this particular pipe, moving from left to right through a constriction in the pipe, we would get a pressure drop that might look like this, and then a recovery as we go downstream. With much higher discharge, we end up with this moderate or even large discharge, we end up with these big drops in pressure, which can get us getting too close to or even trying to exceed the vapor pressure. And when that happens, we don't go further than that. We basically reach the vapor pressure and we start having cavitation occur. Okay, so when we get close to that is when things can get kind of dicey for cavitation to occur. All right, so what I wanted to do is go through this problem. This is not unlike one that you had on your homework. You're going to see another one of these on your new homework starting today. And I just wanted to work through this sort of a novel way to deal with not knowing much about this system and being able to learn a lot as we apply the Bernoulli equation to a couple of different spots. But we're going to note that our limit, our goal, is to find some H that will keep us from cavitation occurring. Okay, so what we're going to do is eventually prescribe a pressure at point number 2 that we don't want to go less than. So we're going to stick in the vapor pressure for point number 2 and say, okay, how big can H be so that we don't exceed this or go below it or get close to it for that matter. All right, so water at 60 degrees is Fahrenheit is siphoned from a large tank through a constant diameter hose as shown in the figure right here. We're already given points number 1, point number 2, and point number 3. And by the way, this is example 3.10, maybe from your book. So I just wanted to walk us through it, but you can go back to that if you have any questions about it or something seems unclear. You can see the book's explanation for it. Find. What are we going to do? We're going to determine the maximum height of a hill or rise H over which the water can be siphoned without cavitation occurring. Okay, the end of the siphon is 5 feet below the bottom of the tank, and we're given the atmospheric pressure is 14.7 psi. The vapor pressure for our water here is 0.256 psi absolute. Okay, one thing real quick. I don't encourage you to ever do this, but one reason that we can siphon or have water move from the tank on the left to the outlet on the right is that look at what happens to our total energy, right? We reduce it so much by going 5 feet below the bottom of our reservoir that basically we set up a gradient so that water wants to move out in that direction. Okay. This is not unlike people trying to siphon gasoline from cars. The beauty of a fuel tank is that, of course, it has to be up off the ground as part of your vehicle, right? And so if you can get a pressure started, and again, this is not something I recommend, but the way that you see it in the movies, or maybe you've seen this happen in the past, the pressure they try to put on, the negative suction pressure they try to put on a tube that is going into your fuel tank is to suck on it. But, please don't ever do that. Sticking in gasoline is not a good idea. But then what happens is you can put your thumb on the end. So maybe there's just another way to do this with like a turkey baster or something. You put it down into, let's say, some kind of basin, a pot or something that's sitting on the ground, and it will freely move out once you get it started. And the reason it does that is because it's more or less this situation. The tank of gasoline is this represented by kind of the water reservoir on the left, and the siphon that you're creating with the tube that goes in and comes out of your gasoline door there, is basically your on the right. Okay, so as long as you have that at a lower elevation and you get the fluid started, you have to get the fluid started. Another way of doing this would be to put a really long tube inside of your gas tank, put your finger on the end of it, pull it out until the level that's inside of it gets down to the ground. And as long as you still have a connection back inside of your gas tank, you can pull gasoline essentially out of your car. So I only mention that because I hope you can all relate to the way in which we move around with fluids in our car, and that's kind of a practical application here. Okay, so on the next slide, I'll do it on the next slide here. We should still have this. Yeah, we have this set up. So let's set this z equals 0 as the bottom of the reservoir here. And we're going to write the Bernoulli equation now among these 3 points. So in other words, P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2 is also equal to P3 over gamma plus V3 squared over 2G plus Z3. Okay, so you're probably looking at that going, whoa, we've been dealing with 6, now you want to go to 9? I'm writing this out. We're not actually going to deal with all of these terms at once, but part of the whole discussion of the energy line and hydraulic grade line is that this should be the case. Whatever 3 points we choose along our system, we should have all the energies adding up to the same value. It's what really it comes down to is sort of what can you predict at any one point. Like if we picked a midpoint between 1 and 2, we may not know enough information about it to really be able to solve the Bernoulli equation between point 1 and some intermediate point between point 1 and 2. Okay, so ultimately we are going to break this into a couple of pieces, but let's just start with what we know that we can eliminate from these 9 terms in this long set of equations. All right, so first of all, we're going to set Z1 equal to 15 feet, right? And Z2 is equal to H, so we don't know what that is. We're looking for that. That's what we need to find. And Z3 is equal to a minus 5 feet. All right, so the difference between the top of the reservoir and point number 3 is actually 20 whole feet. But for right now, part of the reason I chose the datum at the bottom of the reservoir is that we can show you that we can use negative numbers for the elevations and elevation head, and it works out just fine. V1, as we've talked about before, is equal to 0, right? We have no movement of water, net movement of water, sort of at the surface of the reservoir. V2 is a question mark. We don't know what that is. And we also don't know what V3 is, right? So that's also a question mark. However, we do know that because we have a consistent pipe all along the way, a consistent diameter, that V2 is equal to V3. So in a way, we took away one of our unknowns here, okay, in that long equation. Let's look at the pressures now. P1 is going to be equal to 0. P2 is a question mark. We're gonna actually set that with the vapor pressure in a moment, but for now I'm just going to leave it as a question mark. And then P3 is also equal to 0 because we have a jet. Okay, so if I take all of that information, I'm just going to cross out the things that I know go to 0. So that one goes to 0. This one goes to 0. We said at 2, nothing really goes to 0. And then at 3, we know Z3, and P3 goes to 0. Okay, so we've simplified it a little bit. We started with 9, and now we're down to 6. And some of these we already know based on the system. So here's what I want to do. Piecewise, we're gonna work our way through this in 2 steps. The first step is to apply the Bernoulli equation from point number 1 to point number 3. And the reason that we're going to do that is that I think I need to find V3 so that I can apply it to V2. In other words, if I had gone from 1 to 2 right now, I would end up with 2 unknowns. I don't know my V right here, and I also don't know H, which is going to go in here for Z2. So those two unknowns don't help me, but if I eliminate this middleman and just work with 1 and 3, I can figure out V3, and because we said V3 is equal to V2, I can then inform the velocity head back at the other location. All right, so let's do this. So now with all of the things I have, I'm going to boil this down to what's left over. Z1 is equal to V3 squared over 2G plus Z3, okay? That means that essentially I'm going to rearrange this and solve for V3. V3 is equal to, that's a 3, is equal to 2 times G times Z1 minus Z3, and then we take the square root of that entire term, okay? So this is not unlike the velocity terms that we saw the other day and talked about how consistent this was. And now if I inform this or write out all of these values, we get 2 times 32.2 feet per second squared. So this is our acceleration due to gravity. And then we multiply by 15 feet, which is our Z1, and then subtract a negative 5 feet, right? We've got to watch our signs here. And then we take the square root of all of this. When we do that math, we end up with V3 being equal to 35.9 feet per second, which is also equal to V2, okay? So the reason I went from 1 to 3 is because I needed to eliminate an unknown at 2, and now I know what's going on at 2. So I'm still looking for Z2, or what we call H, but now I can write, I know my velocity at 2, and I can define the pressure with our vapor pressure that we had in the problem statement. Okay, so just give you guys another second. I'm going to switch to the next slide to write out the next part of this. Okay. All right, so now let's apply the Bernoulli equation from 1 to 2. Okay. And so remember what we have left over now is Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2, which I'm just going to replace with H. Okay. So we know that Z1 is 15 feet. We can plug that in. What do we do for P2? And we just found V2. So what is P2? So P2, oh, goodness sakes, P2 is equal to the vapor pressure in gauge terms for the water that we have here. So this is going to be equal to, we were given 0.2566 PSI for the vapor pressure minus 14.7 PSI, which is our atmospheric pressure. Oops, PSI. So what that means then is that P2, and it should be a really low value, it should be less than atmospheric, is a negative 14.4 PSI. Okay, and yes, we will convert that to pounds per square foot here in a moment. Actually, I guess, do I have that? Oh, I don't know how that math worked out exactly. I've got it written into a conversion as we go. Okay, so now let me take this Bernoulli equation and inform it, right? So we've got 15 feet is equal to minus 14.4 PSI and then we're going to multiply by 144 inches squared per foot squared to convert that into the right units. We divide by gamma, which is 62.4 for water, pounds per foot cubed. And then we subtract, we add 35.9 feet per second quantity squared divided by 2 times 32.2 feet per second squared. And then we add H. Okay? When you do all of this math, you basically figure out that H comes out to be a maximum of 28.2 feet. All right. So in other words, if you raised the height H, or the height of this hill, as they call it, to 28.2, you would get cavitation. So anything above that is going to give you that low pressure.
Professor?
Question?
Yes.
When you're calculating P2 and you used 14.7 psi, was that atmospheric pressure?
Yeah. Thanks.
So that's the pressure at 0.1, right?
Yes.
I thought that for the 15 equal to that equation to be true, that had to be 0.
No. So what we had to do was get this. This is an absolute pressure into gauge pressure, which means that we had to subtract the atmospheric pressure from it. Okay. So that's why. Yeah. So back on the problem statement, we had atmospheric pressure 14.7, vapor pressure of 0.256 psia absolute. So to convert it to gauge pressure, we had to subtract 14.7.
Okay. Thanks.
Yeah, you bet.
So I have kind of a follow-up question of that. For like is it always going to be given, like the vapor pressure, or like how else would you have to like calculate that?
Oh, this value you could look up in a table.
Okay, so that's like a constant.
Yeah, it'll change with the type of fluid you have.
Right.
It might change with elevation. I can't remember the other control on it, but in
So
any
like
event,
generally it's not something that you would calculate.
right. You wouldn't calculate. The only reason that we did that math was just to get it from absolute to gauge.
Okay, thank you.
That was key. Other questions?
I also have a question.
Mhm.
Why? Can you explain again why we can set P2 equal to the vapor pressure, or why we do it?
The reason we did it is because we were trying to determine the maximum height of the hill that water could be siphoned without causing the cavitation to occur. And the cavitation occurs when we reach the vapor pressure. So we had to convert it to gauge first to know what that was. But then we plugged that in for P2 just to say as a constraint, right? How we need to keep H low enough that we don't get close to that. So we're just trying to find the boundary of what H could be without reaching cavitation. Does that make sense?
Yeah, it does. Thank you.
Okay, you bet. Yeah, one of the things I hope you guys are learning in your kind of across your classes is often you're given these conditions with like, well, without cavitation occurring or without something occurring, and that means that you're substituting in that value into these equations to kind of go into more of a design mode. What is the limit of what we can do here for this particular situation? Okay. Okay, so that ends that. The last thing I have here is a poll question for us, and then I've got one last slide after that to just mention one thing. So let's go to the poll, and I'll get it started here. So water flows without friction through a constant diameter circular pipe that is tilted upward. So like we've talked about before, but now we don't have any change in cross-sectional area. So a circular pipe that is tilted upward, the curve that best describes the static pressure distribution is which one of these? Is it A, B, C, D, or E? And you've got a minute to work through this, to give some votes. What what do we like? Do we like A, B, C, or D? Which way should pressure be going as we go upwards here? As the flow goes upwards. So what do we know about velocity? It's probably staying the same, right? So our velocity head should be constant. But we're changing Z. So what is the response of pressure in this case? Not a ton of responses. Let's see. So, 64. Okay, we're getting there. We'll go an extra 10 seconds here to just make sure everybody can get their vote in. $76, that looks good. 78. How many should we have? 91. So we should have about 88 folks.
There's people in the chat that are saying that they can't answer right now, or it's like taking a bit of time to load or something like that.
Okay. We'll go a little longer here to see if that solves it. If not, I know there was some strangeness with Canvas going down yesterday for some amount of time. So let's see if we get a little closer. Oh, good. I think we're just shy about 3 now. Can we make it there? 3, 2, maybe 2 more. All right. I think Emma, Alexi, and I are the only ones who should be on as participants who probably aren't going to vote here. All right, we'll go up to 2 minutes. And okay, I didn't quite get it. Oh, there it was, 88. Perfect. Okay, so we've got all 5 answers were voted on. So we've got a difference. The 2 lead front runners here are B and D. Okay, so we said that the velocity head v squared over 2g is constant because C-O-N-S-T, not S-N-T. Okay, is constant. Therefore, this should probably be a straight line, right? Because Z is changing from this location to this location. That's a straight change, right? We can follow that that's a straight line increasing consistently. So V squared over 2G is consistent. Then the P is the change in pressure is also going to be a straight line. And in this case, because Z is increasing, then we have to end up going with D in this case. So D is the right answer. And it's because Z is increasing as we go along this flow line. V squared over 2G is constant. Therefore, P has to decrease, and it's going to be linear because the decrease or the increase in Z is linear as well. All right. Great. Well, I hope that was useful to learn from. Any of these curved ones don't really provide us with enough. There's not enough information to know that A or E would work out because we expect that V squared over 2G is identical. All right. So go on to the next slide. Okay, one of the things I just mentioned here in the last minute is to just say that if this is a hose coming out of a wall, the outside of our house somewhere, something like that, one of the things that's not uncommon is to think about how losses occur. So if we put little pinholes in our hose as it's moving along the ground, of course we're going to lose a little bit of water when we do this. So there's not going to be as much water at 0.2 or 0.3 than we have at 0.1. But even if we just sort of ignore that loss for a moment, the energy is going to change as we move downstream when we start to include the losses due to things like friction. The friction between the fluid moving in the hose and the hose walls. And that's often going to be provided. Now our energy line is going to look something like this, perhaps, that we drop off because of these losses that occur. If we were to put in like let's say a turbine or a pump or something like that, we'd have some other discontinuity in our energy line. And so I just